Hello and welcome to this video on the versatile synthesis of alkenes and alkynes by precise residence time control in a flow microreactor. So this is the general reaction scheme we will be looking at today. As you can see, we initially have the lithiation of trans 1,2-dichloroethene to give this 1,2-dichlorophenyl lithium product here. Subsequently, this can undergo two competing reactions. It can either undergo beta elimination to form the alkyne product, or it can undergo electrophilic substitution to form the alkene product here. Before we get into the flow microreactor system, let's first look at this reaction in traditional batch chemistry. Using benzaldehyde as our electrophile, we can see that to form the desired alkene product, the reaction must be carried out at -78°C. To confirm this, we know that if the reaction is carried out at 0°C, no alkene product is formed, as the competing beta elimination reaction prevails and the alkyne product is formed instead. And so we know that the 1,2-dichlorophenyl lithium intermediate is a highly reactive and unstable intermediate, which is hard to control in batch chemistry. However, in a flow microreactor system, we can ensure generation and subsequent reaction of this intermediate before it undergoes beta elimination, simply by precisely controlling the residence time. If we look at how this specific flow microreactor system is set up on the right here, we can see two T-shaped micromixers, M1 and M2, as well as microtube reactors R1 and R2. Combination of N-butyllithium and trans 1,2-dichloroethene into M1 gives our unstable intermediate here. We have the ability to precisely control both residence time and temperature in R1, which means we can optimize the conditions of this reaction to give the best yield. Going back to our earlier example of benzaldehyde as the electrophile, in this system, a residence time of 0.05 seconds at 0°C gives the alkene product at a high yield of 87%. This is very different from what can be achieved in a batch chemistry setting. As you can see in this table, these same conditions in the flow microreactor provide the alkene product in high yield from many different electrophiles. So this system is a clearly robust and versatile system. But it doesn't have to end there. This system can be extended to perform subsequent reactions. As you can see in this example on the right, we can extend the flow microreactor system to now have 4 micromixers, M1, M2, M3, and M4, as well as 4 microtube reactors, R1, R2, R3, and R4. It is important to note that the temperature and residence time of each of these microtube reactors can be controlled individually. This means that we can optimize the conditions for a whole series of reactions, all within one flow system. As with the previous reaction, temperature in R1, which we will call T1 here, is 0°C. Beta elimination of the mono-substituted intermediate here occurs very quickly. So the temperature in microtube 3 does need to be taken down to -78°C, which we can do selectively. It is important to note here that controlling temperature in a flow microreactor is much more efficient than in a batch chemistry reaction due to a larger surface area to volume ratio. So this is still more energetically efficient than a batch chemistry reaction. To accommodate this lower temperature, residence time in microreactors 2 and 3 can be adjusted. So in this example, we have the residence time in R1 still at 0.055 seconds, and then here it becomes 8.2 seconds. And finally here in R3 is 4.6 seconds. These were found to be the optimum conditions to produce the disubstituted alkene here. Again, we can see from this table that this can work with a variety of different electrophiles to give the alkene product, again in very high yields. This exact same setup as before can also be used to produce disubstituted alkyne products instead. All that we need to change is the residence time and the temperature. As you can see here, stoichiometrically, we need 2 equivalents of N-butyllithium in order to go into microreactor 1 here. So in this example, we can form the beta elimination product in the first microreactor here. And the whole system can be run at 0 degrees Celsius, similar to what can be achieved in batch chemistry. Interestingly, there is more than one route to the disubstituted alkyne product. In this example on the right, 2 equivalents of S-butyllithium are used instead to form the beta elimination product in microtube reactor 3. This may be a better idea, as we learned from forming the alkene product before that this monosubstituted alkene undergoes beta elimination very rapidly. Again, the only changes needed to be made are to the residence time and temperature of species in each microtube reactor. If we want to compare these 2 routes to the alkyne product, we can see that in this first example, the residence time, especially in R1, are quite long, at 50 seconds here. Where in the second example, the residence times are much slower, so this is maybe a more efficient example. Both are carried out at 0 degrees Celsius. So we can see from this table that the flow microreactor can be used with a variety of different electrophiles to form many different disubstituted alkyne products, again in very good yield. This really shows the versatility of the system, as both alkene and alkyne products can be produced effectively by precise control of residence time in each microtube. So to conclude, the utilization of a flow microreactor system allows for the selective synthesis of alkenes or alkynes from trans-1,2-dichloroethene. The reaction pathway can be switched by merely altering the residence time and temperature of the system. This provides a more versatile synthesis of alkenes and alkynes than can be achieved in traditional batch chemistry.